So what we proved before was that these so-called generalized Gaussian free fields, they satisfy the Markov property even when we had a set that lived on the metric graph. It does not only have the Markov property just on vertices, which is a consequence because the vertices are just a closed set of my space, but also I could stop midway and I still have this Markov property and this stronger Markov property, meaning that I cannot only, the outside is independent from the inside given the boundary, but additionally I can describe the law of the outside given the boundary. And it has essentially the same law as the beginning, and the main changes are that we add a boundary, so we add like a boundary condition and we change some of the lengths that appeared on my process. But everything else works out the same. So then the question is, are these the only one? So of course they were all the only ones that have Markov property 2, because Markov property 2 makes reference to the generalized GFFs. Okay, we want to say that in a way that they are the unique ones that satisfy this. So how does one go? So let phi be a random function that goes from the graph to R. We define its Lupu Markov lift by tilde by adding conditionally on the values of gamma, conditionally independent Brownian bridges of length t. Of course, I could put any length in each edge, but essentially, if I have chosen the vertices, then in each edge I will just add a Brownian bridge. Okay, so it will give me a continuous function on the metric graph. So we call this the Markov lift, and we just denote it by a phi tilde. And what we are interested is in what are the possible laws that this phi can have. Of course, it can have, if I don't give any condition, it can have whatever law. So we want, so the proposition, maybe this is a theorem. So this theorem, it is being written by Leandro Irene Waigu and myself. Tells you that if phi tilde has the Markov property 1, because the Markov property 2 is already telling you the story. So if I'm just being independent given the midpoints, then phi tilde is a generalized Gaussian free field. So if you have a function such that you make the lift, the Lupu Markov lift, and it has the Markov property, then it has to be a generalized Gaussian free field. These are the only ones. So in a way, it's telling you the Markov property gives you enough equations to essentially characterize your measure up to certain freedoms. And what are the freedoms? The freedoms are the measures you put in each point. So each point can have whatever measure as long as things are integrable. But this is just like a one dimension. Well, it has a lot of dimensions because it's one measure for each point, but it is telling you how the things interact. So it is forcing interactions between them. The only possible interaction is through exponential of minus the Dirichlet energy. Okay, of course, I'm doing this in this generality because one could also put another another Markov bridge, and you would essentially have the other, what I would call like generalized Gaussian free field, in the sense that you are putting whatever Brownian, whatever Markov process you want. Okay? So how does one prove something like that? So essentially what we are going to describe is we are going to describe the law of a point given the neighbors. Okay? So let's fix a point. We call it V. This point may have many neighbors, we don't know how many. I mean, we may be in the complete graph. We may not. We are going to call N is going to be a vector N1 to N. These are the neighbors. Okay, so these are vertices of the graph. And I'm going to choose points here, let's say the midpoint, but it doesn't have to be. I'm going to call them Si. So this may be N1, this is S1, and 2 S2, and N is N. And let's say that this is S. This is the length of this is S1. I'm abusing notation, but S1 has length S1 from the vertex V. Okay? So is it clear, the setup? No? So I have my vertex, I pick a point, and I look just around the neighbors because I already have the Markov property given the neighbors. And what now I want to do is try to understand what is the law of psi of V given these neighbors. Okay? So this feels hard. However, what I'm going to use is that I have the Markov property everywhere. So I have the Markov property given S1, S2, S3, S4, S5. Okay? So we have to write. Now we have to write an equation. So the first thing is that let us describe the joint law of all of these points. So I want to write the probability that phi of V belongs to Vx, phi of n. So when I write phi of n, n is a vector. So I'm going to put is the phi of the first one, phi of the second one, phi of the third one, because I'm just going to care about that one, belongs to dy. So this dy is a vector in n, if you want. Yes? A small n. And I will have phi of s. Again, s is not just one number, it's a vector, and it is giving you the values of the field, and it will be phi tilde. It's giving you the values of the field at each vertex. This one belongs to this. Okay, so this makes no sense because I don't have dx, dy, dc. So I have to take as a Radonico derivative. So according to which object? So according to the law of dy. So I'm going to call this object Q of the xdy. It's just a measure, but it simplifies my life. So this is Q of the xdy. Is this the measure, which I don't know? It is in the field. The field phi is well defined. Okay. Someone gave me the field phi. It has a law. I don't know it, but I can call it Q of dxdy. This joint law times Lebesgue. So I have Lebesgue on this one, and this is Lebesgue in An. Okay. So now here we have to use the fact that phi tilde is the Lupu Markov lift. So if I know phi v and phi n, I know what is the law of phi s. It is just like the point. So if I know the value here and here, well, I just have to draw a Brownian bridge between them. Okay? So what it exactly means in the computations, it means that this Radonico derivative is proportional to the product. It's exactly, for example, proportional equal to the product running from I equal 1 to n of the density of a Brownian bridge of length t at the point S, going from phi v, from x to y I. So the length is Si of Si. So I'm just saying, okay, this is a product, these are independent Brownian bridges, starting from, all of them start from phi v, and they end at different points. So if one properly writes it, this is exactly what this is. So this is the first thing we have to write down. The second thing, so this is just, okay, so this is the first ingredient, and it's just rewriting formally this Lupu lift, Lupu Markov lift. The second ingredient is writing the Markov property. There is nothing else to do, because there is nothing else we have. So Markov property 1. So we do the Markov property 1 for k equal to I didn't want to write this. So S So it's lambda prima minus ds. Okay? Is that the right one? Okay. Yes, so it's, I take everything, I take, so this is my set. And what the Markov property tells me is that the law of the center is given this point, the values here, the law here is independent of that the law of everything else. Do you agree with me that this is essentially what the Markov property tells me? The law is given the values at the boundary, the value at V is independent of the values at the neighbors. So let's write that down. So it tells me that the probability that phi b belongs to dx and phi of the neighbor belongs to dy, given phi tilde at the point S is equal to this. People write given that one equal to C. Okay, this is equal to probability of phi b belongs to dx given phi tilde is equal to C times the probability that phi of the neighbors belongs to dy given phi tilde is equal to C. Okay. So that's the Markov property 1. And now, again, what we are going to explicitly write is this probability measure with respect to Q. So this is a probability measure that is absolutely continuous with respect to Q. And let's see what is the Radon-Nikodym derivative. I don't want to raise the Markov property 1. Now why? Crazy. So this, it feels quite computational, and we are essentially not used to computing, or at least I was not used to compute expected values using mostly the classical probability 1 type of description of probability, of conditional probabilities, but this is essentially what becomes useful. So, okay. So we have the three elements in the joint law. Yes, so we have, with respect to Q of the X. So our main theorem is telling us, our result on conditional probabilities tell us that this probability that phi b belongs to the X, phi of the neighbors belongs to the Y, given that phi S is equal to C. Well, this just will be proportional, so it will be equal. I will write the constant of proportionality. It will be equal to what? It will be equal to the product running from I equal 1 and to n of P, T, Si, running from X to Yi, C, times Q dx dy, divided by, it has to have a partition function. Yes, so the partition function is just the integral over R to the n of this product I equal 1 of n pt si x yi c q dx. I will call this is the partition function that depends on C. Okay? I mean, it depends on C because I'm just integrating on X and Y. And when I'm integrating here, it will be useful, I will add a prime. So I'm adding a prime over the variable that I'm integrating. Okay? So this gives us the conditional probability of this object. So, I claim that if we just need to integrate this to obtain the conditional law, to obtain just the marginal, which is what we need for the second one. So this implies that the probability, so let me write that down. This means that, I will write it here. So you see this equality? Each one of these comes with a C. So I will pass the C to the other side. I have divided C squared here, and I have just one partition function here, so I can multiply, and I will get this following equation. I will get that the partition function times this probability times this object here with x dy is equal to what? Okay, so for the other one, for one I have to integrate on y, for the first one, so I will have integral over, I will write y as all the possible values of y. So this I don't know where it lives. It lives out to the end, but I don't want to write it. 5. And this is n, this same thing. 50 si, and from x to yi, point c, of q dx. And here I have to, I'm integrating over y here, so that's the marginal law, and I have to do the other marginal law times. So I want maybe, yes, times the other integral q dx prime dy. Okay, so in one I'm integrating according in x, and the other one integrating in y. Okay, and now I define q tilde. No, q tilde is a bad idea. Let me define q hat. It will be just another measure. It doesn't have to be a probability measure. Q was a probability measure, but q tilde will be just this object. It's the product of I running from I to n of p t s I. So in particular, it depends on c. And let us know that this main equality we got just becomes c times q tilde is equal to q tilde x times q tilde of b times q tilde of n, where q tilde of b, so this is just a measure on x, just a measure on the point. Well, q tilde of x is just the integral of q tilde dx dy prime over y, and this is the integral over x of q tilde, so x in half of dx prime dy. Okay, so this means that the measure q tilde is a product measure. Okay, this is really great because so the measure q tilde is a product measure. The c, we don't care about it anymore. So I will come here. So let us write. No, maybe I will not do that. So we are just missing one step, which is writing what does q tilde meant. So q, I had q tilde defined on there. Yes. So we know that q tilde is a product measure. So what is q? Which is the law that we were really interested in because it was the joint law of the value at the point together with the value of the neighbors. Q so then q is equal to the product of running from 1 up to n of p t s I running from x yi c to the power minus 1 of q tilde x times q tilde, so q tilde of b, q tilde of n times a constant that we don't care about. Okay? So this is what we have. And now we have to recall what I call the magic formula. So we have two ways of sampling the Brownian motion. This is in the first way. So this comes in the Brownian motion. So this one is equal to pt running from x to yi times p t1. I have to go from x to c, because it's the same thing of going from c to x, times in time s1 from si times pt si t minus si, going from c to y, and all of these are to the minus 1. Okay, so this is our magic formula. We simplify things and we get this pt of xy. So now we define, recall that qv was depending on c, in fact, also qm, but this is our measure mu v. We found it. And now we are almost done. So what is the law? What is the probability that phi of v belongs to Vx given phi of n equal to y? Well, this doesn't matter. All of this part doesn't matter. This will be proportional to just the product over I equal 1 up to n of pt is I x y I, so so this one, pt going to yi. So this is, remember, we are thinking of this as in the Brownian motion, so this is exponential of minus 1 over 2 p phi I minus phi j squared. And when I put the product inside, it's just as a product. Mu v dx. So what did I say? So I learned the following. If I know all my neighbors, there is a way to resample the center point, which is throwing one random variable. So this belongs to R. So this is a measure on R. It's a probability measure on R, because we know it was originally a measure, so it's just a conditional measure. So this is a probability measure on R. And it tells me that if I want to resample the center point, I just need to take one object according to this measure. Okay, that's nice. So what do we conclude from here? We conclude that we can obtain a Glauber dynamic for this object, meaning that I can choose a vertex at random and resample it, and I know exactly how to resample it. So this is a Markov process that it's, if I take a point at random, it's a Markov process that it is aperiodic and irreducible, because I can get to every point. We know we can get to every point because I can stop in the mid things. And so it should have a unique stationary distribution. And I know one probability measure for which this is a stationary distribution. So there is another probability measure with these characteristics, which is essentially, so which one we know it has its characteristic? Well, generalized Gaussian free field where I have mu v at each point. A generalized GFF with parameter mu v. Okay, so it's that one. Yes. So what we learned is that this what we call Lupu Markov property. So meaning Markov property for the Lupu Markov lift. It is somehow characterizing your object, and what naturally appears in the energy is this the mass or the density of your Markov process you started. So we started with a Brownian motion, we get this density. So if we wanted something else, so for example, if we wanted, let's say, a discrete, a continuous in time but discrete in space, we could still do it. And everything we did, we never really used anything about the Brownian motion. We didn't even use the continuity, we used certain continuities of the laws at a certain point to transform almost sure equalities in inequalities, but this can be fixed. Okay? So this is quite a general story, and it gives you ways of generalizing objects to the metric graph in a natural way. And this is the only natural way in a way that can be generalized. For example, another interesting object is what happens if instead of, let's say, looking at a Brownian motion, you look at a Brownian motion on the circle. If you have a Brownian motion on the circle, then in fact, what you obtain, and you put the measures, you put its uniform measures on the circle in each point, what you will get is what's called Wieland model, for example. And with this same treatment, the Wieland model is the only one with these mu v's in particular. And it's the only one that satisfies the Markov property. And you can, of course, change mu v's. You can make them live somewhere else. You could also, instead of looking at Ising as a generalized Gaussian free field, you can think of it as just like a Markov process that is continuous in time and just jumps from -1 to 1. It jumps at rate 1 from -1 to 1. One needs to readjust what the rate means with respect to the length of the vertices and the temperature. So there is one does the computation, but essentially everything works out. One can extend the Ising model to the line to text values -1 and 1 jumping. One can also do -1, 0 and 1. Or one can do the GFF. So there is one can do a Brownian motion. So there are a lot of ways of extending the Ising model. Yes? For example, one could extend a Gaussian free field that takes values in R by making it on the edges takes values in R2. That still works. Yes, you don't have to forcefully take values in R. Everything we did essentially is working for general Markov processes. So now I want to go to the second question. So the second question is, which sets A satisfy the Markov property? Okay? So now we know that the good object to study are these so-called generalized Gaussian free fields. And what we want to do now is find how strong is the Markov property. So which are the random sets that induce Markovian decompositions on our object. And as we know that the Markov property 2 is in a way equivalent to Markov property 1, we are going to always work in the Markov property 2, meaning that I want to be able to describe the law given the set. Okay? I should have erased. Okay. Strong Markov property. Okay. So this is going to be a little more sketchy, but I just want to tell you what's going on and tell you some nice consequences. Okay. So what one needs to do is we want to strengthen the Markov property, and we are always thinking that everything we are doing here is just a generalization of what we are doing in the real line. Yes, so what we're doing for. So we have to do a strong Markov property on the real line. We have to get 3 things, if I'm not mistaken. Okay, so at the first we want to get a filtration. Yes. Second, we have to have stopping times. And third is that we need to get for example, that the Markov process is adapted to that filtration. So it's not only that at time t is independent, but you need something else. No? So if you have, like, for example, an F-Brownian motion is not only measurable, it's not only adapted, but also conditionally on ft, the increments are independent. Yes? And when you have all of these 3 ingredients put together, then you have a strong Markov property. And it's essentially the same. So what is the only thing that we have to realize is that we cannot index our filtration by points. Yes, because our Markov process is not, our Markov property is not indexed by points. It is indexed by closed sets. So we say that Fk is a filtration, it is of course a sigma everyone is a sigma algebra, I think that, but if K1 is contained in K2, the information that I see in K1 is contained on the information that I see in K2. Okay, so now we know that we want to build a Markov. Let me see. Okay, so now we want to say that that our object, our generalized Gaussian-free field, is well adapted to that filtration. Okay, so we say that phi tilde is an F generalized Gaussian free field. If, well, I need adapted. So phi tilde restricted to K is Fk measurable. That's natural. But I also need that phi satisfies the Markov property with respect to F, not only with respect to itself. So phi tilde conditionally on Fk, the law of phi tilde restricted to lambda prime minus k is a generalized GFF on lambda time minus k with boundary condition phi tilde restricted to the boundary. So essentially I have the same Markov property, but instead of conditioning just on what I am seeing on K, I'm conditioning on the whole filtration. Okay, and what I am missing is a stopping set, which is quite natural. This is what's missing, so what? So we said that A is a stopping set. So okay, so usually I write something belongs to Fk. So I would usually be the time smaller than t belongs to my random time smaller than t belongs to Ft, and here I will have to just write A containing k belongs to Fk. So everywhere where there was a t, I replaced by k, and everywhere where there was a smaller or equal, I replaced by a subset.
Do you need to worry about the topology of the analyzer or not? Really?
Yes, so sets are closed, and the topology I'm using for closed sets is the Hausdorff topology.
Okay.
It's a good question. I wanted to hide it under the carpet, but yes, that's important. So this, and if you know this for all k, this you know A. So this is something generating. A is a stopping set stat, and of course we also need to define the filtration associated with A. It's just all of the set theta such that theta inter A containing k belongs to Fk. So I hope these things become natural to you. It is like really the way to extend the Markov property from one dimension to whatever space. And what I claim is that this is enough. So this is the sufficiently good enough setup to be able to describe the Markov property. Okay, so theorem. So the strong Markov property tells you that let phi tilde be an F generalized Gaussian free field, A and F stopping set, then conditionally on f of a.
No, sorry. Now, on the boundary now? Or you're conditioning on the...
No, I'm conditioning on f of a, yeah, because I'm looking at the Markov property too. I'm conditioning the whole set.
Yes. Sorry.
The law of phi tilde restricted to lambda tilde minus a is a generalized Gaussian free field on lambda tilde minus a with boundary condition phi tilde restricted to the boundary. Okay. And let me do a sketch of proof. Because this is quite classical. So what you do is as follows. First, you assume A takes finitely many values, or takes countably many values, but it's finitely many values. And in this case, essentially, you can write phi restricted to a to lambda minus a as a sum over k, which are the possible values it can take of phi restricted to lambda prima minus k, indicator function that k is equal to k, and then one needs to take conditional expectation given fa. Okay, and one essentially uses the Markov property and properly describes this, and it will work here. So it is a computation that if you have done the one-dimensional case, it is fundamentally the same. The main difficulty is understanding fa. Okay, then 2 is approximating a by something I like to call an, which is essentially just an 2 to the minus n. You are fattening to the next dyadic, let's say. So then you get finitely many of them. You have to show that this one is a stopping set, and the main idea is fattening is always a stopping set in a way, but not thinning yourself out. No, if you thin yourself, it's like you can never be one street before I get to a traffic light, but you can always be one street after I pass a traffic light. So this is the same idea here. So then now you have the Markov property, and now you have to take limits. So to take limits here, you take an converging to a. So you have to show that the filtration of an converges to the filtration of a, and this and everything else comes from the continuity. So everything is continuous here, both on the lengths and on the points where I am started. So if I start a Brownian bridge at a point instead at x plus epsilon, and instead of running it from time t, I run it from time t plus epsilon, I'm still quite close, let's say, in the topology of. So it cannot be uniform. It is the weaker one, Scorvots. Yeah. So that's essentially the proof. It is really a copy of the one-dimensional case. And now I want to discuss two things. So why this is useful, and I want to discuss if these are the only ones. So let me show that they are useful. So I want to use two examples. So the first one is a formula, and the second one is FKG inequality. Okay. So the first formula. Corollary 1. Assume that all the measures phi b are symmetric. Yes. So this ensures to us that our generalized GFF is symmetric. If I put minus phi or phi, it has the same law. Then the 2-point function of the sine. So if here we have to be careful, because this may take value exactly 0. Sine of 0 is 0. So my sine is either minus 1, 1 or 0. Is equal to the probability that x is connected to y by a path in which phi prime is never 0. Okay, so 2-point correlation functions can be read out of the sines can be read out of connectivity properties of not going to 0 of this object. And the proof is just that you define, I have to define a random stopping set. So I have to define a stopping set will be the connected component containing x of the set of phi different non-zero, phi tilde different non-zero. Okay? So you start at a point, then say that this is the graph. You have y here and x here. They don't have to be on the vertices. And now you have to convince yourselves, because I'm just going to do the drawing, that if you explore here until you hit 0, this is a stopping set. Because and what is the filtration? The filtration is a natural filtration. Yes, and I can see whether the set is inside or not if I know the values inside the set. And then, well, then what is the value of the expected value of sine phi x sine phi tilde y given f of a? Well, if they are in the same connected component, they have the same sign. Do you agree with me? So if x and y are on the same connected component, they share the sign. Because this thing is continuous. So this is indicator function of a. And on the event that they are not, so on the indicator function of a on complement, then I have outside a generalized GFF with boundary condition equal to 0 here. So this is symmetric. Yes, so then it's 0. So then it's just indicator function of a. Indicator function that y belongs to a. Yes, sorry. So if they are in the same connected component, then it's 1, and if they are different 1, then the sign is symmetric, so I can see. Good. So the corollary 2. So allow me to put, so the corollary 2 is going to be FKG, okay, but I'm not going to completely write FKG. So FKG is a direct consequence of monotonicity on boundary conditions. So I have to put boundary conditions, okay? So I have a generalized Gaussian free field with 2 boundary conditions. So let phi 1 and phi tilde 2 generalized GFFs with boundary conditions. So boundary conditions just mean I fix some vertices and I fix their value. B1 bigger than B2. Then, then there exists a coupling phi tilde 1, phi tilde 2, such that almost surely phi tilde 1 bigger or equal than phi tilde 2. Okay, so we'll construct a coupling between. So if they have one is that's bigger than the other, I can construct a coupling where this is always kept. And this implies FKG inequality quite directly. Okay? So also one could get FKG inequality directly from Collins's condition in a way, but this is what I call this is a geometric interpretation of why it works. So we are going to see this coupling, and the coupling is going to be quite. So proof. So I'm going to start phi 1 tilde independent of phi 3 tilde. This is boundary condition B1, boundary condition B2. Okay? So I started independently. This is not my coupling. However, I can now I can use the filtration. So I will use the filtration of the both of them. Okay, and I still have the Markov property according to this filtration, which is a bigger one, which is nice. That's a nice thing of adding filtrations. And then I define the set A will be the connected component or the union of connected components containing the boundary of the set phi 1 of x bigger or equal to phi 2 of x. So if we come back to our graph here, so we have a boundary, we have two possible boundaries, and then at each point, what I'm going to say is that I'm going to go, so B1, let's say phi 1 is still bigger, and phi it's not bigger anymore. Okay? And then that means they are equal because of continuity. Here the same. Okay? And I claim that this is a stopping set. If I have a set K, it's easy to know, and I know the values of phi 1 and phi 2 inside the set K, I know whether my set belongs to that or not. Okay? So this is my set A, so that means that phi 3 is equal to phi 3 restricted to A plus phi 3 restricted to A to lambda tilde minus A. Okay? So conditionally on A, phi tilde 3 lambda tilde minus A is equal in law to phi 1. You agree with me? These two are equal in law because they have the same boundary condition. I stop exactly when they have the same boundary condition. So now this is equal in law to phi 3 tilde restricted to A plus phi 1 tilde restricted to lambda tilde minus A. It's like you take up two Brownian motions independent, when they hit, you run them together. This is the same thing I'm doing. And this is phi 2. And if I'm on A, phi 1 was always bigger than phi 3. If I am on A complement, they are equal. So then I have monotonicity. So allow me to say something for the last 3 minutes, which is that these are the only ones you can get. This is something one is not used to see in a basic course on Markov chains. One is not always used to see that the only ones that generate a Markov decomposition are stopping sets. So essentially I will finish the metric thing, and it will be quite nice because next time we are going to discuss the random planar maps. Sorry. So it looks quite unlikely that I managed to do something on the continuum, but I will at least comment probably at the end what it is. So, proposition, take a coupling of phi tilde, so this is a generalized Gaussian free field, and A, which is a random set, a random closed set, such that conditionally on phi tilde restricted to A, phi tilde restricted to the complement is a GFF, is a generalized GFF. Okay, it has a Markov property, no? Right, GFF on lambda tilde minus A with boundary condition. Then I will be able to find a filtration such that phi tilde is an F generalized GFF and A is an F stopping set. So the only So that means that our theory is complete. We are not missing any object. If you just, we are not missing any Markov, anything that decomposes Markovianly. And I know I am over time, but let me just do the sketch of proof. So you define the filtration is explicit. F of k has to have phi tilde restricted to k. It has to have the event A containing k. But then it will not be a filtration because it has to be monotone. So it has to have the event A, indicator function A. Okay. This is not enough by some stupid reasons. So this is the filtration. So it's obvious. So let me just with colors. It is obvious that this is an f-stopping set. It's direct the adaptability. The hard part, I will not do, and I will not do even in the planar map case, but it is the only part I know it's well written. Well, maybe there's two parts, but it's in our paper with Pablo and Luis. Is this satisfy the Markov property with respect to. So this is the hard thing to do, and it is a little bit technical, but it is somehow manipulating the sigma algebras and properly conditioned. So that's what I wanted to tell you this time. Next time we are going to somehow, if you don't remember this, it's not that important because I'm going to work in another model and I'm going to try to do the same thing, but now when the domain is random also, and you want to have the Markov property not only on the field, but on the field together with your graph itself. And that will be the game.